Hello, I am Rocío Carratalá-Sáez from Universidad Jaume I in Spain, and I am going to present the work we submitted to the 21st IEEE International Workshop on Parallel and Distributed Scientific and Engineering Computing, whose title is Tiled Algorithms for Efficient Task Parallel H-Matrix Solvers. This work has been done in collaboration with Mathieu Faverge, Grégoire Pichon, Enrique S Quintana-Ortí, and Guillaume Sylvand. I will begin this presentation by talking about what H-matrices are and how the LU factorizations are performed of them. Then I will talk about the previous work and the alternative approaches that exist to these structures. And lately I will present our approach, named H-chameleon, the results and conclusions we want to highlight, and I will also give some lines about future work. In this slide you can see on the right a typical H matrix. In red, the dense blocks, and in white you can see low rank blocks and the corresponding rank written inside. It's observable that there are different block sizes and there's a nested structure in there. So how do we move from an original matrix, for example a dense matrix arising from boundary element methods, to an H matrix like this one? First of all, we need to define cluster trees of the matrix indexes, one for the rows and one for the columns, and then we create a block cluster tree which will define a partition that applied to the original matrix will give us the hierarchical matrix. As an example, I have put a really simple one here on this slide, and you can see that to determine where to stop partitioning, we need to choose an admissibility condition in advance. This admissibility condition, when it's fulfilled, it will tell us that the block in which we are evaluating the data is non-representative enough to be compressed, which means to be converted into a low-rank block. It's also needed a minimum block size to stop partitioning when we reach it. So, combining the admissibility condition, the partitioning criteria, which in the previous slide was just partitioning 2 by 2 each time, and the minimum block size, we can create an H matrix out of a, for example, original dense matrix. Which one is the benefit, or which of the benefits of employing hierarchical matrices? Even though we compress the data, so it means we lose part of the accuracy, the important thing is that we can achieve a log linear order both in terms of storage and computations. Details about this can be seen in Hackbook's work from 1999. What has been done previously regarding H matrices, and which are the alternative approaches? First of all, let's remember that the LU factorization of a matrix consists on decomposing it into the product of two matrices, one lower triangular and one upper triangular, whose product will give back the original matrix. In this slide, it can be seen the classical block right-looking algorithm for the LU factorization. In each iteration, the LU of the diagonal block is computed, and then the column and row panels, L and U, respectively, values are computed by solving the triangular systems of equations. Before proceeding to the next iteration, matrix-matrix products are performed to update the remaining values in the matrix. A natural extension of this algorithm, just taking into account that in an H matrix you have different block sizes and also a nested structure, was proposed by Ronald Freeman in 2013, and this is the LU factorization algorithm which is nowadays employed for solving H matrices LU decompositions. In previous works, I tested the behavior of task-based parallel programming models in scenarios where we have H matrices. I observed that we can reach up to a 42 times the speed up when using a maximum of 48 cores. And details about these works can be seen in the references you can observe in this slide. Here on the plot, there are the speedups for a matrix of dimension 42K arising from a 3D boundary method application and employing different admissibility condition beta criteria 0.5, 1, and 2. No WD or WD means that we employed or not weak dependencies. What are those weak dependencies? When trying to operate with H matrices, there are some difficulties, such as data location and the recursive nature of the algorithms, mainly. Why data location can be a problem? The issue is that when we store an H matrix, the only data that you can be sure you have it in continuous positions of memory is the one belonging to a leaf block. That's a non-partitioned block in your matrix. So, depending on the operations that are performed, if they involve different block sizes, logical partitions of the bigger blocks will be needed to be able to perform the operations. Moreover, as the algorithms operating with H matrices are usually recursive because they need to move through the different levels of the hierarchy, this implies that when implementing a task-based parallel programming approach, nested dependencies are needed. And the problem is that with the well-known OpenMP programming model, this is not well supported. So we needed to move to OMPSS2 and the associated runtime Nanos 6 to be able to leverage new features such as nested data regions dependencies, early release of tasks, and weak dependencies annotation to be able to deal with all these and reach the good speedup I showed in the previous slide. So, talking about previous work, there's a big effort needed to be able to deal with all the tricky parts of H matrices and their associated algorithms. That's why different approaches have popped up. Some of them are based on the runtime system which is employed. Here I put 3 examples. The first of all refers to the implementation of the HMatOSS library on top of StarPU, and the main issue with this one is that it ends up having a large number of dependencies. Recently, there was a semi-automatic DAC generation proposal, but the issue is that it's necessary to trim the DAC from unnecessary edges. Another approach suggests using fake dependencies, which is very similar to the weak dependencies I proposed in my previous work. And the issue with this is that it implies introducing recursively the missing dependencies to be able to fulfill all the dependencies between the tasks. Different alternatives to common H matrices are based on the structure itself, on the way the compression is performed concretely. For example, there's the block low rank or the block separable formats, which base the structure on performing a regular tiling of it. This way, the concurrency degree is increased, but it's true that they are not as efficient as H matrices are. There's another recent approach named lattice H matrices, which tries to combine the regular tiling benefits with the hierarchical benefits. Our approach is similar to this one, and I will explain it in the next slides. So let's go to talk about our approach HCamelo, which is the basic idea of our approach. Similarly to lattice H matrices, what we do is to partition the original matrix into regular tiles. This way, we will be able to achieve a high concurrency degree as it's achieved with, for example, block-low-rank formats. Inside each tile, we compress the information by creating an H matrix, a whole H matrix inside each tile. Our approach is based in two existing libraries, Chameleon and HMathOSS, which respectively offer a whole set of dense linear algebra operations and all the operations and functions needed to operate with H matrices, create them, and extract all the information. We will employ StarView runtime system to tackle multi-core architectures. The clue point, the key of our work, is that we need very few implementations. Actually, for example, for Chameleon, we need to slightly modify the descriptor and create a new tile struct to be able to handle the new formats, which include low ranks and H structures. Regarding the link between Chameleon and HMathOSS, we need to create our own descriptor to be able to move from one library to the other and keep all the structure information which is needed by them. And regarding HMathOSS itself, we need to include in that one some wrappers to be able to move from C++, which is the language in which HMathOSS is written, to C, which is the language employed for Chameleon. Lastly, of course, we need a new clustering algorithm to be able to perform the tiling partitioning and then inside each tile to create an H matrix. Having all this ready, we are done and we can offer the community H Chameleon library. So how does H Chameleon library behave? To study it, we chose a test case which is really similar to real industrial applications, and it consists on choosing a cloud of points on the surface of a cylinder. We will offer results regarding complex case and also real case. The equations defining each of the cases are presented at the bottom of this slide. All the tests have been performed in Plavrim cluster, which is a Bora cluster, each node equipped with 2 Intel Xeon Skylake Gold 6240, 36 cores available running at 2.60 GHz, and 192 GB of memory. We have used Intel MKL 2019 for BLAS kernels. In the plots, real double and double complex precisions will be shown, respectively marked with a D and a Z. We will offer different dimension results, and for them we have always chosen the best tile size out of a whole set we tested. It's important to remark that we employed from 1 to 36 threads, but in the case that we use StarPU, this is when we test H Chameleon, we use up to 35 threads instead of 36 because we leave one thread available for the runtime. To evaluate H Chameleon, we decided to compare its performance to the one offered by HMath. HMath is a proprietary library from Airbus, and this decision was based on the fact that the whole set of sequential algorithms that define HMath are exactly HMathOSS. This implies that H Chameleon and HMath will share the way they treat low-rank and hierarchical structures. We did not only want to evaluate the performance, but also the compression ratio and the precision, because this way we can see if having a tile plus H instead of a pure H matrices structure affects the compression or the accuracy that we can get. In these plots, we represent HMath results in dashed lines and H-chameleon in full lines. It's observable that the compression ratio is very similar for all the dimensions we tested. So we can say H-chameleon compresses more or less in the same degree HMAT does. The same is applicable for the precision. Here in these plots we can see that the differences are less than 1 order in all the cases, so we can say that the accuracy we can get with H-chameleon is more or less the same we can obtain with HMAT. Regarding the performance results, we now show the execution time when solving the LU factorizations. Here in these plots, we show the results for the smaller dimension we tested, 10K, 20K, and 40K. In red, we represent the HMAT results, and in green, blue, and purple, the H-chameleon results. We offer 3 different results for H-chameleon because we tested 3 different scheduling policies. It can be observed that H-chameleon is very similar or even better when we are in real double cases, and slightly worse in complex cases, especially when employing a small number of threads. If we go to bigger dimensions, we can still see that H-chameleon is better when we use a big amount of threads in the real double scenarios. However, the behavior in the complex case is the same we were observing before. H-chameleon is slightly slower. To conclude, I would like to highlight that we have seen H-chameleon offers a good compression ratio and a good precision compared to what we can achieve with HMAT library. And in terms of performance, we can say H-chameleon offers a good parallel performance. In double precision, we are generally better than HMAT, and in complex precision, even though it's true that when we go with bigger matrices, H-chameleon is slightly worse, in small matrices employing a large amount of threads, H-chameleon offers more or less the same execution time, or in some cases it's even slightly better. The big conclusion out of this work is that our tile-edge-based approach behaves well in this context, and it's competitive with the performance that can be achieved with pure H matrices on multi-core architectures. It only remains to talk about future work. As part of our plans, we would like to offer more performance comparisons, probably employing bigger matrices in them. We are also interested on evaluating what happens if we use different structures, or maybe a cylinder with different dimensions. And of course, we would like to, at some point, go to distributed memory. This has been all from my side. I hope you have enjoyed this presentation, and I would love to receive your feedback from it in any of the emails you can find in this slide. Thank you very much for watching.